Hello everyone, my name is Jinyan Xu, and I'm from Zhejiang University. Today I'm going to present MorFuzz fuzzing processor, a runtime instruction morphing enhanced synchronizable call simulation. And this is a joint work with Yiyuan Liu and other co-authors from Zhejiang University and the City University of Hong Kong. Modern processors are too complex to be bug-free. However, it is not until the recent meltdown and Spectre attacks that make people realize that their processors are not as perfect as they thought. In fact, if you look at the errata documentation, you will find that our processors are never implemented as expected. Almost every generation of the commercial processor have dozens of errata. One of the most recent examples is the AMD Zen bleed bug. These errata are bugs that are found after the chip is released, which means most of them have no plan to be fixed. They just live on your processor and strike at you at the moment they are triggered. They will give you incorrect results, unexpected behavior, and freeze your system or even cause security problems. To automatically find these unexpected corner cases, researchers take lessons from the software community and start to apply fuzzing to processor verification. And this diagram shows the basic workflow of processor fuzzing. In the first step, the fuzzer uses the seed to generate a bunch of assembly code as the input of the processor, and the generated instruction are further compiled into a binary that the processor can understand. And during the generation, the fuzzer will also mutate the seed or the assembly code to try to explore new paths or logic in the hardware. And then, in the next step, the fuzzer starts to simulate the design and the test, and the report is simulation coverage. We first use a RTL simulator to translate the source code of the processor into an executable software model. And during the simulation, the software model will fetch instructions from the input and execute them. And just like the software fuzzing, the software model is also instrumented to collect coverage information, and the input generator will use this coverage to evaluate its mutations. And in the final step, the fuzzer needs to figure out whether the DUT behaves correctly or not. To achieve this, we introduce an ISA simulator as the reference model. By comparing the state of the DUT and the reference model, we can consider all mismatches as potential bugs. However, existing fuzzers are limited by several challenges that prevent them from effectively and efficiently fuzzing processor. To explain these challenges, we use a test case generated by the DifuzzRTL, one of the state-of-the-art processor fuzzer. In this test case, all green code blocks are payload instructions that are used to fuzz the processor. The first challenge is the complex input grammar. For example, if we want to test the load unit of the processor, we need to generate a bunch of load instructions. To generate a valid load instruction, we first need to have an address as the operand. However, we cannot directly change the processor state, like the value of a general purpose register. We can only use extra instruction to calculate this, the target address we want. And second, we need to test all kinds of load instruction, including different access lengths, signed extension or unsigned extension. And we also need to test those reserved OP codes, especially those OP codes that cannot be represented by assembly code. Now we have operands and OP code. We still need to make sure the generated instruction have valid semantics. For example, if we generate a load word instruction, we need to make sure the accessed address is 4-byte aligned. And the second challenge comes from the control transfer instruction, like the branch instruction or jump instruction. This means the generated instructions are never guaranteed to be executed. The problem is that suppose the escaped code blocks contain some valuable mutations, but the executed code block do not contribute to the final coverage. The fuzzer will consider all these mutations unhelpful and will eventually discard them. And the second challenge is the model implementation differences between the DUT and the reference model. The SA simulator is just a functional model of the processor. it cannot accurately simulate the behavior of the peripherals or the cycle-accurate events like interruptions. And besides, there are also some permitted implementation differences in the specification. For example, the property of the CSR SATP is write-any, read-legal, which means that even if the same value is written into the CSR, the value read-out may differ depending on their implementations. These implementations will introduce false positives and prevent the fuzzing from triggering deep states. To solve the above challenges, we propose MorFuzz. The core idea behind MorFuzz is to dynamically mutate those instructions that are going to be executed, which we call instruction morphing. To achieve instruction morphing, we have designed a new input structure, the stimulus template. Instead of using multiple instructions to calculate the operand, we use a special load instruction to access a randomizer in the test bench to get a random value with the desired data type. We call this special load instruction magic instruction because they are able to set the target register with the desired data type in just one instruction. And we also replace all payload instruction with the template instruction. The template instruction are blank instruction with dummy fields. They only contain necessary information to calculate the memory layout of the stimulus template. And during the runtime, MorFuzz will morph this template instruction into meaningful and diverse instruction streams. To achieve this, we introduce a morpher in the circuit. Typically, it is placed on the wire that connects the processor fetch unit and the decode unit. The morpher will hijack template instruction fetched from the input and performs field level and semantic level mutation on it, and send the morphed instruction back to the decoder. And we eliminate implementation differences by state synchronization. To avoid introducing false negative, we divided the state comparison into two stages. In the first stage, we only compare the control flow information to make sure the DUT and the reference model are executing the same instruction. And in the second stage, we compare the write-back data. If the results do not match, we further analyze whether it is an implementation differences. If yes, we will synchronize the DUT state to the simulator to make the simulation continue executing. And this is the overview of MorFuzz. Different from the existing fuzzer, we dynamically morph instruction we dynamically morph instruction to effectively get fuzzing. And benefiting from instruction morphing, we can use runtime information to generate instruction with better semantics. And during the simulation, the dummy template instructions are morphed into diverse and meaningful instructions. And we also run an SA simulator in parallel to verify DUT's behavior. When a legal implementation differences is detected, we use state synchronization to eliminate the false positive. We evaluate MorFuzz on 3 open-source RISC-V processors, including CVA6, Rocket, and Boom. And MorFuzz found 19 bugs, including 17 new ones, and 13 of them were assigned CVE number. All of these bugs are confirmed by the developer. And for the coverage, MorFuzz is able to achieve more coverage and also faster compared to existing random instruction generator and the state-of-the-art processor fuzzer. In conclusion, MorFuzz proposes new techniques to dynamically fuzz processor and eliminate false positives. And MorFuzz detects previously undetected bugs in real-world processor and achieves better performance. Moreover, MorFuzz is open source and ready for you. You can get more detail from the QR code or the link. That's all. Thanks for your listening.